Hello, my name is Mitchell Falgoust. I'm a fourth year PhD student here at UTA. My research advisor is Dr. Peter Kroll, and I'm presenting machine learning interatomic potentials for pyrolysis of polysiloxanes and properties of SiCO ceramics. So polymer-derived SiCO ceramics see polysiloxanes as precursors. We typically take these materials or these polysiloxanes and heat them in inert conditions up to 400 to 1,000 degrees Celsius to induce pyrolysis, producing a ceramic. There's also continued reactions such as phase separation of the SiCO glassy phase into silica and silicon carbide, as well as a free carbon phase, and continued heating results in carbon thermal production. So SiCO ceramics have these properties listed here, which are useful. A couple depictions of some of those properties. The goal for this project was to develop a machine learning interatomic potential for SiCOH using moment tensor potentials, in which we hope to simulate with DFT-like accuracy, low temperature behavior, high temperature behavior, and reactive conversion of polysiloxanes to SiCO ceramics. And examples of some of the structures appearing in that compositional phase are shown below at low and high temperatures, respectively. So our method is machine learning with MLIP2, which is a software implementing moment tensor potentials for machine learning. DFT calculations are performed with FAST, and DFT, we essentially save the energies, forces, and stresses and use those for the fitting. And then classical MD and our simulations are carried out with LAMPs. So for validating our machine learning interatomic potential, we use a test set to see how well our potential performs on configurations outside of our training set. And we look to compare forces because we are concerned with how our temperature behaves at high temperature, how our potential behaves at high temperature. We also look at the impact of complexity. So in all, we notice higher forces arriving, or higher forces are attained at higher temperatures where reactions happen. Complexity is essentially great for accuracy, but we want computational efficiency as well as accuracy. So we pick level 12 since it's good enough with accuracy much faster than the other levels. And we notice that our potential does a really good job with fitting high forces, as the worst errors don't appear in the high force section. It appears in the center of the distribution in both cases. So for low temperature, we produce the vibrational density of states, which act as an analog to IR and Raman spectroscopy. So some experimental overlap here in which we can actually computationally observe or computationally produce experimental comparables. So what we notice is that in terms of low temperature vibrations, MTP does a great job of replicating DFT. And with that validation, we're able to apply this model to other systems, such as the one given below, which is an SiCOH with a large graphitic carbon phase. And we can trust the results that we get from it because we have validated against DFT. We isolated a couple of reactions which are very important in the conversional process, such as production of gases and the formation of SiCH to Si linkages, which are important for the formation of the glassy SiCO phase. Speaking of the glassy SiCO phase, we looked into the mixed tetrahedra and the distribution of them according to heating simulations, in which we observed that they approach the ideal distribution of mixed tetrahedra. And these results are something that we can see in silicon NMR experiments. And going into large-scale simulations, we're able to simulate 1 million atom systems for 10 nanoseconds, or for up to 10 nanoseconds for less than 2 weeks, which is very fast. So in all, we have an accurate DFT-like potential. It's capable of long-term simulations of large systems, and it's useful in the calculations of vibrational spectra as well as reaction simulations. There's some room for improvements, lower activity of water and methane and SiCO coordination defects, but we have solution. We can improve or omit or get rid of these imperfections with more configurations, including reactive intermediates into the training set and other structures. So in all, we developed a machine learning interatomic potential for the conversion of polysiloxanes to SiCO, and it produces DFT-like accuracy even at high temperatures. Thank you.